Okay, welcome back to day two of ontoNexus Forum 2025. In this afternoon session, we have two tutorials planned. Uh, the first one is a tutorial called OML Foundations and Tutorial. Um, then the second one will be a tutorial about Empire. It's called Empire Foundation and Tutorial. So in both tutorials, you will see a deeper dive into ontological frameworks, and I hope you find it interesting. I'll try to make the OML one a bit. It has some bit of interactivity, so I hope you help me out when it's time to do that. Okay, um, so my outline for this tutorial, I'll first give a brief overview of the OpenCSAR project itself for those who are not very familiar with it or its history, its mission. Then I will be I will be focusing on the ontological modeling language, which is the lingua franca of OpenCSAR, the main formalism, ontological formalism. And then I have a couple of tutorials that we will deep dive in, and then I will overview the rest of the tutorials that you can find online. First, a bit about the OpenCSAR framework. So, as you may know, it's a framework for ontological modeling and analysis. It allows you basically to define your business domain, whatever this domain could be. It's not specific to system engineering. It could be any domain that you like. And then once you define the vocabulary, then you can start modeling facts about the world using this vocabulary. And then once you have created the model, then it gives you tools to analyze your model and derive insights from the model, because the whole point of modeling is analysis. So, and we hope with this project to improve the state of the practice in fields like system engineering in particular, focusing on rigor, agility, and automation with this raised vision, which is the theme of this forum. The framework is mainly developed and maintained by the Jet Propulsion Lab, but it's not only the only developer. There's a huge list of contributors that their efforts went into improving the framework to what it is today. And the framework within JPL has been used to support model-based system engineering. It has been used on several of the NASA missions, including the ones you see below, Mars 2020, back in 2014-15, Europa Clipper, Psyche, and Sample Return. The project is open sourced, and it basically represents the foundation upon which an organization can build its own system engineering methodology. It gives the building blocks for that. It's an open source project on GitHub, and it has an active blog where you can see posts, papers, tutorials, and various contributions by the community members. So here's a bit of the history of OpenCSAR. It started at the beginning as a plugin to SysML, actually, to Cameo Modeler, and it was used on the Mars 2020 project. And then in the time frame of the Europa Clipper project, it started becoming ontology first approach. But it took a bit until 2018, where we took what we were doing at JPL and open sourced it as OpenCSAR. So in JPL, we always refer to it as just CSAR. outside, it's OpenCaesar. And it has helped also the Psyche project and currently the sample return retrieval lander. So the framework or the project supports three main use cases. The first use case is if you want to natively model in ontologies. So ontology is the first kind of artifact you author yourself with vocabulary, and then the framework gives you the tools to author information ontologically. Another use case, which is if you want to analyze engineering models that are not ontological, but you want to analyze them with some ontological rigor. For example, SysML in Cameo, for example, or in other tools, you want to analyze that. So you could export the information from those tools or represent them in an ontology format. Then you can have access to the reasoner and queries and other things. And the third use case is to use it to build the digital thread. Basically, you can develop an ontology representing the business domain that you want, and then map from different engineering tools into that common representation so that you can do interchange and you can do integrated analysis across otherwise siloed data sets. So the use case I'm going to focus more about is the first one, which is using ontologies natively to describe your information. So how does OpenCaesar help with this in this regard? If you're a practitioner who created system engineering models before, you may resonate with these pain points that you often see. That people sometimes they don't know how to actually get started modeling because there is no well-defined methodology. Or it could be that there is a methodology, but the tools they work with are not helping them follow that methodology. People often work in groups, and so it's natural to expect collaborative features in the tools you work with. A lot of the tools today do not have these nice capabilities to allow you to collaborate properly. Compare, merge features, for example, ability to fragment your model and link them, version control them, and whatnot. We often also build models to analyze them. So you expect that modeling tools will come up with analysis tools also built in, or once you model, you can analyze. But sometimes people, when they model, they keep modeling, and then they do not have a clear vision of how to derive analysis. So that is a missed opportunity. And it's often when you want to configuration manage models, you want to be clear who authored what kind of information, what's the version of this information, the provenance. That's very important to have. You also want to generate these gate products. At the end, you want your model to be consumed by others, and you may want to target their needs with custom viewpoints. You don't want to create these custom viewpoints by hand. You want it automated. So for all these pain points and others, we need something better. So the OpenCaesar framework introduces this vision of a modern modeling environment, and it focuses on 7 functions. And I don't know why the numbering here is messed up, but there are 7 functions. Starts by representing models in a rigorous format, and for this, OpenCaesar chooses the semantic web ontologies as the rigorous way of representing information. It gives you facilities to do authoring, to actually help you create the models, to help you configuration manage it in the modern repositories like Git, where you have all the collaborative features. Federation, which is the ability to split up some models and then to create them, and you will see one of my tutorials about that. And then how do you check models? You have to analyze them. So that's why OpenCaesar provides reasoners, query abilities, and finally ways to create viewpoints or reports or gate products so that you can share the model information with other people. And at a very large scale, that's how the OpenCaesar framework is architected, you find on the left-hand side the authoring side of OpenCaesar. It allows you to either work in ontologies natively in an OML workbench, and you saw maybe if you attended the previous sessions examples of that. Or if you have other engineering tools, we can also bring them to ontological format with adapters. Adapters help us translate. And then we put all these data sources of a project into Git, into a Git repository, so you can version control them. Then we have in the middle the analysis, where we convert these representation into OWL. We run it through a reasoner to check its well-formedness and consistency. We make sure the data is well-formed, because you don't want to proceed to do any analysis if your model is not consistent, for example. Once we verify it's consistent, we put it into a knowledge base, and then we start the other analyses that we want to do. In all these analysis cases, we produce reports or results that we want to share. Some of the reports are meant for humans to work with. Some of them are meant for other analysis tools to work with. And some of them are interactive. The user wants to actually to ask their own questions. So something like a chatbot would be convenient. And finally, you want to keep versions of these artifacts in some artifact repository so that you can retrieve them later and you know which version got produced by which commit and things like that. So that was just a brief overview of what OpenCaesar is, what it provides. At the center of OpenCaesar, this ontological format is the language OML, ontological modeling language. So the language was this was not the first choice of OpenCaesar. It was actually OWL itself directly. So we started modeling in OWL, but we quickly realized that it takes a lot of effort and it requires a lot of experience to actually get the OWL ontologies right. So what we found ourselves do, what we had to do is to write a bunch of audit rules to check that the OWL we produced is correct and not only correct, but will actually give us the reasoning results that we expect. As you may know, the OWL ontologies, they support open world assumptions, which can sometimes give surprising results when you do reasoning, if you are not careful in properly adding the right axioms to make the results of reasoning make sense. So for all these reasons, we thought, okay, why don't we create another language that already takes into account all these considerations as first-class concepts, and that led to the definition of ontological modeling language. We also had another objective. We want to facilitate the process of creating models with ontologies, and the Eclipse modeling framework at the time was a very popular tool for that. When I go to modeling conferences, almost 90% of the work is based on Eclipse modeling framework. So to leverage also this tooling ecosystem which was mature, we thought also of implementing OML using the Eclipse modeling framework. So it's just an implementation choice. OML itself is defined as a grammar without the EMF. EMF is the reference implementation, I would say. But that gave us a lot of facilities in building nice workbenches and tools, leveraging compare merge support, textual editors with Xtext. So it gave us a lot of leverage to provide quickly an environment for OML. And with OML, we basically do two levels of modeling. You do vocabulary modeling, where you describe the concepts and relations and properties of your business domain. And then you use that to describe your system or the knowledge that you want to describe using that vocabulary. So that's basically the workflow. A bit about the syntax of OML. So I described vocabularies and descriptions. So it's not surprising that the abstract syntax of OML also is split that way. There is the vocabulary abstract syntax and the description abstract syntax. And in vocabularies, what we talk about are terms of your vocabulary, the nouns and the verbs that make up your vocabulary, the classes and the properties, basically. And additionally, we have inference rules allowing you to automatically infer information that is not asserted in your model. So once you've built the vocabulary, then you need to start writing to describe your system with instances of these classes and using the terms of the vocabulary. So that's why descriptions is all about instance modeling, and the facts that you assert there uses the vocabulary, the types and properties defined in your vocabulary. And at the top, you can see two things called bundles: vocabulary bundle and description bundle. So this is the concept we introduced. It's another ontology that imports your vocabularies or descriptions, but it attempts to add extra axioms to make sure that the reasoning result is what you would expect. For example, if you have two types, like a cat and a dog, you don't want the reasoner to infer that some individual, some instance is both cat and dog in the same time, because you fail to say that cats are not dogs. It will add such axiom automatically for you if it cannot see any common subclass of both classes, for example. So the textual syntax of OML, it's a small grammar. On the right-hand side, you see the textual syntax of vocabularies, where the vocabulary is declared with a unique namespace, a prefix just to make it shorthand. It could import other vocabularies, and then you start defining the terms of your vocabulary. You can also extend terms from other vocabularies that exist elsewhere. So you can reference terms that is not declared in the vocabulary, but you want to say something more about them in this context. And finally, you can write rules. These are the inference rules that help you say things without actually saying them. You actually write the production rule. If some pattern is detected in the model, then you can infer this other pattern. So this makes you very concise when you are building your model. You don't have to say everything explicitly because it will be inferred by these rules. And the bundle is just another ontology that groups a bunch of vocabularies and then applies this algorithm that generates these extra axioms to make the reasoner give proper results. Similarly, for descriptions, on the right-hand side, you see a description with a unique namespace, and a prefix. But you have to declare what vocabulary are you going to use in this description. So you can declare vocabulary you intend to use, and then you start creating instances, facts of the word. I have a car called car one, and car one, its color is blue and its weight is this. So this vocabulary you're using to actually assert facts about the world, you are getting it from some vocabulary, and now you're trying to actually say the facts that you want here. And these facts will be grouped under this namespace, which is convenient because now I can ask two engineers to state the facts from their perspective, and they could keep their facts in their own namespaces. They don't have to mingle them in the same model if they don't want to. This way we can keep clean provenance of information. This is the facts from engineer X or engineer Y or team X and team Y perspective. Yeah. So you have a UML background? Okay. So a vocabulary is like the UML class diagram, and a description is like the object diagram, where you create instances of things typed by the classes. Yeah, so a dog one is color yellow. So dog one is a dog. A dog is a class. Dog one is an instance of the dog, and then color is the property of the class dog. Now you're giving it a value yellow in this case. Yeah, and then we also have this notion of description which is sorry, a bundle of descriptions. Why is that important? Imagine that you are developing a system and you want to you have variants in the system. For example, you're considering two kinds of engines that in the car. So if you're just working on one model and you put these two kinds of engines in there, it will be hard to analyze the car in these two cases. You have to kind of build two different cars in order to one with engine one and one with engine two. In here, you can actually keep the same one engine, but how you describe the engine, which type, what are the characteristics, these statements that you are making about it can be put into different descriptions. And okay, so which ones are you going to analyze? That's determined by which description you put into the bundle. So you can create different description bundles for the different analyses that you want to do. And in each one of them, you can decide which set of facts you want to include in your in the data set that you are analyzing. So it works quite nicely. For example, if you said object X can have a maximum of two objects of type Y, okay, this maximum, it needs to have a context. In the context of what? The bundle kind of gives this context. It's look at all the facts from all the descriptions in this bundle and consider those only and nothing more. So it helps you kind of define a boundary of the world that you are analyzing. All right, so this is the syntax. And we developed also graphical syntaxes, and you've seen some of it in the previous presentation, that although it's a textual language, convenient for putting in Git, config, managing it, pull request, all these things that you can do with source code, you can do with ontologies because they're textual. But if you want to visualize, we also have notation, and they are in the form of diagrams. So all the OML workbenches support visualizing the ontologies with textual, and we intentionally made it UML-ish like, so that if you're coming from a UML background, you will be familiar with these notations.
I get.
Yeah.
Question. Just remind me, are relations able to have properties or attributes or something like that?
Okay, good question. So we have two kinds of relations. One relations are like what is equivalent to UML, an association class, where it's the relation is an entity by itself that can be characterized by its own attributes. And we have the version of relation that's a simple link, that it's not an object. So we have relations that are objects and relations that are just simple links. In fact, if you, for example, describe a relation between a customer and a product, the customer buys a product. If you don't want to say anything except that, you can make it a simple link. But if you want to say this purchase that happened is on this date for this price, and you want to give more information about it, then you reify it, i.e. you make it an object. And now, because it's an object, has an identity, you can actually give it attributes. We call this relation entity as opposed to just relation. Any relationship, when you model vocabulary, you think you decide, do I reify it, make it an entity, relation entity, or I'm just interested in the direct link and that's it. I'm not characterizing it. So you can make it either relation or relation entity. But in both cases, you still say, what's the domain of the relation? What's the range of the domain? Is the relation transitive, reflexive? All these properties you can say in both cases the same way. But in the relation entity, you just give the extra feature. You can create an object and specify properties for it. Of course. Yeah. So for example, you would say transaction is a relation entity between a customer and a product, and one of its attribute is the date of the purchase, for example. In fact, this particular pattern of relation entity is not a first-class pattern in OWL itself. In OWL, there is nothing called a relation entity like that. It's actually in OWL, they only have object properties, which are the simple relationship. What we had to do, we use the class, a regular OWL class, as to represent the relation entity that between the source and the target, and we then give that class some properties. So that same thing, if you want to do it in OWL, you will need several statements to say the same thing that you can say in OML in just one go. So OML it adds a layer of abstraction, giving abstractions that are useful for modelers in the use case. In fact, what you see here is the mapping, how OML abstractions map to corresponding OWL abstractions. Are you familiar with OWL? That's kind of the mapping, but in some cases, one relationship, one object on the left maps to several statements on the right. Okay, so you can create ontologies, vocabularies, and descriptions. But how do you actually go about making this work or useful in a project? So before you can describe facts in the project, the descriptions, you need to say what vocabularies do you have that your project will work with. And when you say that, when you want to say what vocabularies you work with, it doesn't have to be just a single vocabulary or a vocabulary about everything the project want to do. You can be strategic and fragment your vocabulary. You can compose it. You can say, for example, I will start by picking an upper vocabulary where I define my design patterns. And a very useful design pattern system engineering is, and they've alluded to this yesterday, that component present interface. Interface can be joined by junctions. This basic pattern, fundamental that you can componentize, expose interfaces that can be joined, is a very fundamental design pattern system engineering. So you want to pick a vocabulary, an upper vocabulary, high-level vocabulary that has a pattern like that. Then in your disciplines, mechanical discipline, electrical discipline, you specialize that pattern. You say, in electrical, my component is called an assembly, and the interface is called an in-circuit, and the junction is called a function, and so forth. You can specialize it. The nice thing about specializing patterns is whatever analysis you apply to the upper applies to the lower without having to repeat it again. So this way, you can actually create a bunch of separate disciplined vocabularies that get unified through a common upper ontology. And then you develop your analysis on this level, and then you can enjoy it in every discipline that specializes it. Okay, so, but now if we have a bunch of separate discipline ontologies, mechanical, electrical, we still want to give the project a consistent set of vocabularies to work with. How can we have all these disciplines like siloed like that? The answer is to bundle them. You create a vocabulary bundle where you say, I'm giving to this project a bundle of vocabularies that includes discipline 1, discipline 2, discipline 3, and sometimes, of course, these disciplines are not siloed. So you may have additional ontology, additional vocabularies that actually relate these disciplines together. They say, what we call in this discipline this, we call it that in that discipline, or this relationship goes from this discipline to that discipline. So all these ontologies, you put them together into a bundle. You apply the bundle algorithm, which is kind of like a closing the world algorithm. Now this bundle is ready to be used by a project. Well, if all projects are the same, they will just take your vocabulary bundle and run with it. What happens in practice is that some projects have unique cases, unique circumstances that you did not even anticipate before. What do? You allow them to create their own vocabulary bundle by adding extra vocabularies over what you provide them. Say, okay, I provide this, but the project can come and say, okay, but I need this extra property here, extra property there. You can actually add it in another vocabulary and then create another bundle, project-specific bundle right now that takes the first bundle and adds to it. Now, with that vocabulary bundle, you can start specifying your descriptions. And when it comes time for analysis, you want to put these descriptions into different analyzable data sets, description bundles, and then you can invoke the reasoner and the analysis tools on each one of them. So I call this the developing an ontology stack. Okay, so how do you do this in practice? We're using the OML workbenches. And the production workbench we have is Eclipse based. Remember, I said the Eclipse ecosystem is huge. So we started with that. And with this, you can develop, we provide out of the box capability to write the ontologies in a textual way or visualize them in a graphical way. However, this is good if you are kind of ontology savvy oriented. But if you are like an end user system engineers who really is sitting every day and they don't have necessarily, they don't want to learn all these things, then what you can do as a methodologist who's helping this engineer, and usually every company who's doing this needs to have some team called the methodology team. This is the team that actually creates this ontology stack for the projects they are helping. And hopefully, if the organization wants the same stack used in all the projects, they can collaborate and define one stack and then give it to every project. They can extend it, as I said, but it's better to have as much common as possible because this reduces the relearn curve for everybody who's maybe involved in multiple projects. So to reduce the bar, to lower the bar for system engineers at the end, we give them user interfaces that hide the ontology in the background. These user interfaces, they could look like diagrams, tables, forms, anything you like. So the user will not feel like this will not feel foreign to them. And under the hood, these UIs are actually creating ontologies, following the vocabulary. So we actually do this at JPL. We design such user interfaces and we give it to the missions. They don't see OML at all in this picture, but they still enjoy the benefits of ontological modeling thanks to the reasoner, something to all the analysis pipelines that we give them. So we recently started aiming to have another workbench that's web-based because web platforms are becoming popular. VS Code was identified as a promising platform to build web tools on, but also we are looking into Obsidian as another choice of a web platform to realize an OML workbench in. So both are still experimental and we are making progress. Once we release this, that will probably become the production, but we will still support Eclipse in the same time. So, okay, you are an engineer now. You have the OML workbench. You are working with it. How do you actually share and manage? And we put our models, the OML models, into Git. So instead of inventing our own database, our own version control systems, all these things, we actually use what exists. So Git is the world-class configuration management platform. It already has the notion of branches, the pull requests, all these blows and whistles exist. So we are leveraging it. OML is textual artifacts, perfect use case for being put into Git. However, we still need a way to analyze the model, to actually run reasoner and queries. So since we are piggybacking on the semantic web stack, we allow using the reasoners that exist in the open domain. For example, the pellet reasoner, that's the main reasoner we're using. You can run it on the OML models to check their consistency, and then you can load the OML model into databases that also exist in the open domain. We use an open source version called Fuzaki, but you can use also production big servers by Amazon and other big companies. But a very important thing we did here is we need to publish the ontology. We need to do release management of ontologies. What does that mean? We need to make a read-only cut of an ontology and give it a version number and preserve it in history, such that it's not immutable. It's immutable at this point. We want the ontology version 100, and then we make a change. Ontology version 101, 102, 112. We use semantic versioning actually to label our ontologies, and these follow the same pattern in software. If you did a small typo or something, fixed a small bug, you make a patch release. If you added new features, but you did not break something, you do a minor release. If you broke something, remove the concept, refactor the big thing, then it's a major release of the vocabulary. So, and we push these read-only versions to an artifact repository like Maven. The nice thing about Maven, it already supports semantic versioning. So we can just make a version and push it there. And then on the other side, if you are a consumer of the ontology that got published, you declare what you want to depend on with a Maven coordinate. Very convenient. You say, I want version 1.x. 1.x means I care that it's the first version, the first major version, but I don't care what's the minor and patch. Give me the latest. X is like, give me the latest. Or you can be very specific. I want 1.0.5, and then you get what you want. So every OML project, if it's meant to be reusable, it pushes its version into Maven, and then the consumer can declare what version of Maven they want, and they get it. And you can see how this ability is very helpful for federation use cases. You are a project, you are developing it's a complex version of a space mission, a car product, and you have all these kind of teams, all these kind of disciplines. It's not very nice to have everything in one repo and have a few committers on it. You actually want to federate, you want to distribute this workload. So in the methodology side, you say, okay, you guys are experts in mechanical, you are in propulsion, that's in thermal. Everyone gets their own repo to put their vocabulary, and then you declare your dependency on other people. So for example, you can have one for the design patterns, and then another one for every discipline, and then a third one for the bundle. And everyone has the authority, and you can version control them separately, but in a coordinated fashion with the Maven dependency. Similarly, you can federate also your system models the same way. You can break them down by subsystem, by discipline, by team, and keep producing versions and keep depending on other people's work by semantic versions. This way, you can feel free to experiment and create a branch and do some experimental work while not breaking others, because they are not seeing these changes, because they are locked into version 2 while you are developing the next version 3. They will not see it unless they decided to move to version 3. And because they did that, they decided to go to a major version. Now they know that they are having to deal with refactoring because they chose to go from one major version to another. They expect breaking changes. But if they said, we want the latest features, but we don't want to break things, they can lock the major version and then say, give me the latest minor version. Or they're not even open to new features. They're done with testing. They don't want to add new features, but they just want the bug fixes. They can lock major and minor and open the patch and so forth. So it makes it actually the same experience software developers are developing software like this. So it makes it the same. Okay, you created, you configuration managed, then what? As part of supporting the agility of this approach, you don't want to wait 6 months for people to review your ontology. You want to always know what are the issues in the ontology. Everybody's on the same page. We know we haven't completed the work yet. It's still work to go, but if you just hide it, if you are the only one who's checking this ontology on your machine, you could be doing all kinds of things, right? Nobody knows until the review time. You want it centrally managed. So what you do is you put all these checks, all these reasoning analysis pipeline into CI/CD, continuous integration delivery. Every time you commit, there is an analysis pipeline stands up, checks your ontology, produces reports so that the team is aware of the status at any point of time of this work. That's very useful. And these reports that you produce, they have provenance information, what commit they come from. And the nice thing about this approach is that you put your analysis pipeline in the same repo as your models, so they get version control together. So if I'm using analysis pipeline version 1 and then ontology version 1, then in a future the ontology evolved, but the analysis also evolved. They evolve in the same time, the same commit. So if I checked out a historical commit, I'm also checking out the historical analysis tools at the time. So I can reproduce the same results back then. And otherwise, I would be using the latest tools, but historical commit, things will not be matching. So by having the analysis pipeline in the same data, that's a great approach of managing the evolution of both of them together. So that was just a quick overview of OML itself as a language. So now we will do one of the tutorials. And I'm picking here a simple domain that everybody would understand. I'm calling it the basic family domain. The simple domain, I said, there's a person. Person could be a man or a woman, subclasses of person. And a person can have parents. There's a maximum 2 parents, and it can have children. And then the relationship to a person to a man is a father, and the father subsets parent. It's a special kind of parent. And similarly, a mother is a special kind of parent. And you can have a maximum 1 mother and a maximum 1 father. When you don't see multiplicities in OML, this means 0 to star, 0 to infinity. That's the unrestricted default. If you want to restrict the 0, if you want to move it up to minimum 1, minimum 2, then you can say that. Or if you want to restrict the upper range from infinity down to 5 only, a car has 4 wheels. Okay, I want to be specific, 4 wheels. You can do this without restricting. So this means you can have 0 child or unlimited number of children, which makes sense. Where I think in UML, the default is 1 instead of 0 to infinity. So when you don't say anything, the default is 1. Here, the default is 0 to infinity. Okay, so what you see on the right-hand side is the textual syntax of this vocabulary that you see visualized here in the graphical syntax. We see a person restricting the parent to maximum 2 instances. A man is a kind of person, one kind of person. And you see that a parent is a relationship from person to person. It's the inverse of parent is called child. Forget this, it's a typo. Let me remove it. And it's symmetric and irreflexive. What does that mean? Symmetric means if I said A is actually it's asymmetric, sorry, asymmetric. Asymmetric means if I said A is a parent of Y, it doesn't make sense that Y is a parent of X, right? So it's asymmetric relationship. So which means the reasoner, if it found X is a parent of Y and also Y is a parent of X, it will complain to you saying this relationship is wrong. You cannot say that. Not even if you just asserted it, but also if it could infer this relationship from other facts in the model. It's also irreflexive, which means a person cannot be a parent of themselves. That also doesn't make sense. So if the reasoner concluded that some person is a parent of itself, there's something wrong. Okay, and now a mother is a subclass of parent, so it's a special kind of parent, and it's also from a person, but this time to a woman, unlike person to person. So you specialize the range of this. So if you said X is a mother of Y, or sorry, that X has mother Y, then the reason I will conclude this Y must be a woman, because mother is from a person to a woman. Even if you did not say that explicitly, this is what it can infer because of this domain and range specification. But it's also functional. What does functional mean? Maximum 1 value for this property in the context of the domain. So a person can have 1 woman as a mother. If it inferred somehow that X has the mother Y and a Z, it will say, well, let's be careful. If it also concluded that Z and Y are different individuals, it will complain. But maybe Y and Z are not the different individuals. Or even though they have different names, they might be aliases to each other. So the reasoner, without any knowledge, it may say, okay, fine, X and Y are mothers of this person because because Y and Z are the same person. So how do you tell the ontology, no, they're not the same person. I actually mean different. You have to say this explicitly. You have to say, and Y is disjoint from X. It's different from X. There's an axiom to actually say this is different from this. If you say that, then there's a problem here that, okay, he has two mothers now, two real different individuals a mother. But without saying this, it could say, okay, maybe they are the same, that just aliases to each other. Okay. Functional means you only expect a maximum one value of mother for a person. Person, exactly. If you asserted two mothers, or either asserted or it inferred through rules, inference rules, that there is two mothers, X, Y, and Z, it's now at a decision point. Is this bad or not? So it will think, okay, do I see anywhere in your data set something that says Y is not Z? If it's so that, then you have two mothers. That's wrong because it's functional. But if you did not say Y is not Z, then it will not complain. Then you find just Y is also known as Z. So and that's actually a benefit of some of these algorithms that we turn on. You can have something called the unique name assumption, which it's a general way of saying to the reasoner, hey, by the way, any name that you see different, actually treat it as different by default. So if I said Y and I said Z, these are not the same person. You can explicitly tell the reasoner that. If you don't, then it may not conclude what you wanted to conclude. Okay, so with this vocabulary, very simple one, let's create a model of that vocabulary, like a particular family here, right? And I'm using these iconology. The actual OML is on the right, but you can use this as a way to visualize it. So man and woman, and then a father like a blue arrow and a mother like a red arrow. And here is the model. Now you want to analyze this model. You want to see what's happening with this model. You want to ask and I'm calling it the nice family just then. Okay, is the nice family model consistent? Is it well formed? What do you think? Can you spot a problem in this family? No, missing is not consistent. And say consistent. It could be missing. Is it consistent? Missing is okay if you don't configure the ontology for missing to be inconsistent, and we didn't. So inconsistent usage of the very simple vocabulary here. This is the vocabulary. This is it. And this is the model.
Is it that is the purple arrow about mother?
Yeah, the purple is mother, the blue is
So why
father.
is Peter a mother of Clara?
Why what? Peter,
Why is
where's
Peter
Peter?
down there?
Peter.
And
No, this is okay. It says it's his mother is Clara. So that's fine.
Oh,
Peter's mother is Clara. So that's the mother axiom.
Maggie, can you hear me?
Yes.
Is it that Dave and Cattell were cousins?
Okay, so you mentioned cousins, but our ontology so far doesn't have cousins, right? It just talks about parent, child, mother, father. That's it. So in that context, is there any problem?
are you saying that we're failing OML Jeopardy?
No, I'm asking you a question. Here is a simple vocabulary, very simple, and a simple model. Can you spot the problem if there is any problem?
I would say the problem is that Elaine's parents are first cousins.
Well, unless you state that explicitly as a rule, that's not a problem to the reasoner. Okay? So, in fact, so far this family is consistent. So, but now let's add this axiom. Fiona has a father, Albert. Now, is it consistent? It has two dads, right? Or who has two dads? Fiona has this and this, has two fathers. And why is that bad? Because we define it to be functional. Yeah, you said functional means maximum one. Now you have two. That's a problem. So it will complain about that. However, it actually will not complain unless you say unique name assumption. Because it could be that Elias and Albert are the same individual. You didn't say they are different, so it will not complain. But if you say there is a unique name assumption, now, okay, now Elias and Albert are really different people. Now there's a problem. Without that, it's not a problem.
The unique name assumption asserted where?
When you set up the reasoner,
Yeah.
So you have two choices. You either add the assertion yourself. You say Elias is not the same as Albert, explicitly like that, as an axiom in your ontology. But if you had to do this everywhere, you have to say, and Elias is not Paul, and Paul is not Isa, and then there's a lot of axioms. As a shorthand, you say, I want to use the unique name assumption. So the reasoner will infer that every name that's unique is really unique.
And when you say this is in the reasoner, is that in some aspect of, it's not the
It's a
description?
setting. It's a setting of description logic reasoner
Okay.
to make the assumption that that every unique name is really unique.
But actually, there's another way we do it in OML, which is by making, for example, like a name property functional.
So this is another feature in OML. If you don't want to enable because if you enable this, it will be global. Every element is unique across the board. However, if you want to be specific, you want to tailor which one is unique, which one is not, OML provides something called the key property. You can say, for example, that the social security number is key property of a person. This means two people with the same SSN are the same people, are the same person, just known by different names. But if they have two different SSNs, they are different people. So you can use this trick. You can pick some properties and say these are key. And it doesn't have to be one property. You can have 4 properties are key. So the tuple of 4 is key to this person. You can configure. So this way, it's not that everything could be everybody, or it's that every unique, you can configure actually who is unique, who's not by using key properties.
All right. Can you describe what functional is? I missed that. I know you said it said.
Functional
one,
means
but-
a maximum 1 value. Like a person has a maximum 1 mother.
Okay.
He can have 0 mother, but if he has mother, it can only be 1. It cannot be 2 mothers.
So how did you come to, and this is deep in the weeds, so if it's not relevant, please, you can tell me that irrelevant, you can ask me later, but like going from it's only 1 to the word functional, how does that? Okay. Okay, okay.
It's the function definition in
Okay.
math,
Oh.
where input and
okay.
output.
Yeah. Okay,
Yeah.
okay. Got it.
Right. Okay. So what if we added this axiom instead? We made Jane Father Cattell. So what's the issue? It's blue.
So the issue is that we're saying that Cattell, which is a woman, is the father of Jane by definition of the ontology.
Well, if you define the ontology and you said, if you And let's go back to the ontology. So you said man is a subclass of person and woman is a subclass of person. And because you said this woman is a father, the reason I would say, okay, this woman is also a man now. Which without saying that men are not women, it's good. It still can conclude that this individual is both a man and a woman. You have to tell it man is not women. And therefore it will know, oh, okay, there's a problem here. We didn't say here, right? So it will actually conclude in this case that Cattell is a man and a woman, is a woman and a man in the same time, and will not complain because you didn't say men are not women. However, if you now enabled our special bundle closure algorithm that automatically add an axiom for you saying a man is not a woman, then it will complain. And we apply this algorithm when we detect two classes that don't have a common subclass. Imagine that you really wanted to say men and women. So you can create a special subclass of both. Any common subclass. And that's automatically, we apply an algorithm to all your classes, finding all these cases and asserting these beliefs are disjoint.
But then you can actually review the point about this bundle closure is that it's just applying a principle, and because now we actually the result is still like another OML ontology, you can actually review and check, well, do you agree with this? And you could potentially say, no, it's okay for a man and a woman to be the same person somehow, and therefore decide to omit that particular conclusion and leave other disjunctions in there. Right, right. We call it a policy-based analysis.
And in fact, if you think this is not applicable in some case, this is often a case where if you define the class not representing a real concept, but a class that represents some capability. For example, you can say named element. A named element is not a real thing, right? It's just a characteristic of somebody. So it's like what we call it a mixin type. It's not a real concept. It's a mix, and that's why these kind of things we call them aspects in OML. So in OWL there's no distinction. Just they're both classes. But here we say no. Some classes are not real concepts. They're really aspects. So you can say named element, blue things, anything like that, which is more like, sounds like more of a capability than a real concept. You declare them as aspects, and as aspects, they don't get subject to this algorithm that calculates the disjunction. It will not say that this is disjoint from this, and we leave this the aspects not subject to this because we want to make them extensible because they are capabilities. They're not real things. So we leave them from this closure algorithm automatically when you declare. So when you declare your vocabulary, you have to think: is this a real concept, or is this more like a capability, an aspect? And you model these as aspects, you model these as concepts.
That'll be fun to explain to the systems engineers community at large.
Yeah.
I have a quick question.
Yes.
So is there a way to like embed these configurations for your like query engine into the source code for your project?
Yeah, we call them so these choices of what is the set of things to run algorithms on is the bundle idea.
Okay.
So for example, if you said, if in this ontology you said man is not a woman in this ontology, this you closed the word for extensibility. You just said man is not a woman. So any extension for that will have to inherit this axiom that you just said. We don't explicitly say these things in vocabularies to make them open. When you put them into a bundle, we run it on the bundle. Now you could in one bundle just leave it like that, men are not women. But in another bundle, you add a third subclass of both, and you say, oh, some people are women and men at the same time. In that bundle, they will not be disjoint. So it's up to the bundle which ontologies, what classes you put. So you can have, you can define chains of bundles where you incrementally add axioms based on the circumstances, and then every bundle will have its own set of closure algorithms that will calculate the proper reasoning.
Might be putting the cart before the horse here, but we looked at an example where you explicitly define the ontology objects. Large data systems, right? I'm already thinking things like BOM relationships. I have the data already. I would like to turn that into OML code.
Okay, that's, I think, Kareem, who left the room. He worked on a problem like that. He was given a document which has a bunch of statements encoded, and somebody wanted to analyze this ontologically. So how do you go from statements to something you need to analyze? You need to infer a vocabulary. So they developed an AI, Gen AI, that given a bunch of axioms, can you infer a reasonable vocabulary out of this? And they have a starting point vocabulary that they can just tweak until they get what they want. So the AI here is assisting you, looking at the data, try to infer relationships from the data and building a starting point vocabulary for you to improve on. Okay. Okay, so given a vocabulary that you have and a data set that's not related to the vocabulary, you want to make the link. Say which instances are instances of which classes in the vocabulary. Yeah. Yeah. So the nice thing about ontology is you could assert anything and then you can add other axioms in other modules. So you could have a complete definition of instances that don't have types. You can say, I have a Brian and Clara, and you didn't say they're men or women yet. In another ontology that extends that, you can say, and by the way, Brian is a man and Clara is a woman. So starting with a set of axioms that are not annotated with typing information, how you add this typing information, it's either manual in another ontology or with AI or some algorithm that you can develop that will generate these extra axioms. They become another ontology. You don't have to merge them with the first ontology. You can keep them separate if you like, because maybe you want to run another AI algorithm, produce a different opinion, and then you can compare, for example. Okay. So now let's enlarge this vocabulary a bit more and add these two relationships. Cousin, and now who was referring to the cousin relation. We have a cousin relationship and we have a sibling relationship. A sibling is a person to a person. It's now symmetric, right? Because A is a sibling of B means B is sibling of A. So you only have to say A is sibling of B, and the reason will infer the other way. And irreflexive, a person is not a sibling of themselves. Cousin is also symmetric and irreflexive. And now we want to add, I don't want to infer cousin, or I don't want to assert myself cousin and sibling relationship, because a reasoner can do that. So I can write a rule of inference. I tell, okay, if X is a parent of, if X has a parent P, and Y also has a parent P, but this X and Y are different people, infer that X and Y are siblings. If I omitted different from, then we're back to the problem, right? It could be the same, just an alias, okay? And infer cousin. So the X has a parent P1, and Y, different person, has a parent P2, and these two parents have the same parent themselves, the grandfather, no, or the grandparent. And the X and Y are different people, and the P1 and P2 are different people. Then you can infer they are cousins. You can just write this and then ask the reasoner to infer. It will infer who's sibling of who, who's cousin of who automatically for you without having. That's very convenient for queries. Imagine you want to query who's cousin of who. Everything is already inferred. You can just ask a simple question, give me the cousin of X. It will immediately get you the cousin of X without having to do all the work or the crunching, because it already did it in one go in the reasoning go. And if you asserted yourself manually that some random X is a cousin of Z, if that is in contradiction to some of the inferences, it will detect that and will report back to you. So let me see if I have, yeah. So in this case, for example, who is the sibling of whom in this nice family? What do you think? Who are the sibling groups here? Based on you looking at this model. So who do you say are siblings? Fiona, Dave, Clara, and Brian have, okay, so is it the only group? Leah and Elias are siblings. Are they siblings? No, okay. So let's see the answer. Elias and Leah and Elias, they are siblings of each other. And this group that you mentioned, Fiona is a sibling of these folks. Brian is a sibling of this. Clara is a sibling of that, and Dave is a sibling of this. These are all the axioms that the inferer will infer for you. It will give you this result automatically for you. And who's the cousin of who based on this ontology? Ketel is the cousin of. Okay. Is there any other cousins? Or is it the only cousins? Alan and Peter are cousins? Hmm? Jane is the cousin of who? Elaine and Peter? Okay, let's see. Right? Peter and Elaine and Jane are cousins of each other. And this is what gets inferred as, so Ketel is the cousin of all these folks, but all these folks only have Ketel as their cousin, right? So now if we added this relationship between Dave and Leah and we said they have Dave. In fact, this should have been yeah, it should have been like purple, right? So in this case, is it consistent? It will be actually consistent. So the issue this introduces, it makes Ketel a sibling of Dave, but it's also the cousin of Dave because we saw earlier it was a cousin of Dave, but now because of this, it's also a sibling of Dave. Is that a problem? If you didn't say cousin and siblings are disjoint, they are not a problem. But in this case, if we added explicitly Ketel and cousins and siblings are disjoint, they cannot be the same, you cannot have them in the same way, then it will conclude it's a problem. So but here you see they are cousins because they share the same grandfather. So they are cousins. and they are also siblings in the same time. So they match both patterns, which is no problem if you did not say cousins cannot be siblings. But when you add this explicitly with the property disjunction, then the reasonable concludes, sorry, they cannot, there's a problem here. Right. So I hope with this example, you can see how a reasoner can be helpful. And if we could be, this is a very simple example, very simple vocabulary. Imagine engineering, system engineering vocabularies with all kinds of things going on. You need the help of a reasoner to really check your data is consistent or not. Can easily make mistake. You can easily under constrain the problem and end up with bad result in reasoning. So that's why using a reasoner is, and having semantics, be particular what's allowed, what's not allowed, will pay dividend in your project.
I mean,
And-
certainly as part of a discovery of your system and what your assertions about how you're thinking about the pattern, like I would not have caught that. And certainly even the reasoner returning some result like that, I'd probably be scratching my head for a while and
Yeah.
understanding why, because it is not intuitive to me.
Right,
Um,
right.
But so that's, especially when we're talking about spacecraft.
And when,
systems.
yeah,
So-
when there's a huge complexity of vocabularies and
Yeah.
all kinds of things, you could be surprised what it could infer for you
Oh, no, that's what I'm saying is.
from your data.
Because, I can already have enough arguments about words as it is, and I can imagine what this
Yeah.
hopefully will
This
Uh,
this is
at least give them a path towards reconciliation because it's very logic based.
And this is also a great example of about how, such a simple pattern uh, uh, brings out how important it is to be really clear about what it is you want to capture, what questions you want to ask about the model. Because, the semantics can be different
Oh,
in
yeah.
different situations.
Certainly. Yeah, the questions are important. That's for sure. I agree.
But more importantly, what Maggot showed is an example of what some folks in the formal methods community call the small model hypothesis, in that often it suffices to have a small model, like in this case, you have, I don't know, 10, less than 20 things and relations, to find maybe surprises or examples of things that make sense, right? And so part of then the process of vocabulary development, like describing, ought to include a kind of like a small model hypothesis experiment to check with maybe machine generated examples or some things to find out, is this well formed? Is this the kind of thing that you think is acceptable? If it is consistent, for example, do you accept this kind of model as being what you really intended to capture? And so that could help discover the need for disjointness and functional restrictions and, unique name assumptions, things of the sort.
It's interesting. It also helps to, this kind of stuff I could spend a couple of days on my own just modeling something to death, and then it serves little purpose. So it's like doing the small model arrangement also feels like a way to kind of come at it in the context of questions without spending a long time at it. If you get a lot of value out of a small model.
Right. All right. So that was tutorial one. I will skim through the second one. But I will then leave you with a bunch more like self-paced tutorials. So the second one is about model federation. And that's a topic that should be very familiar to system engineers who work on big projects at least. So this is the pattern I like to project first. Imagine you're working in a system that's too big to work on yourself by one team or one person, and you need to federate. You need to divide these into pieces, get several teams or people to work on them, and then you want to integrate their result. So The pattern says before you embark on this, you have to start with a methodology. You have to define a bunch of vocabularies for that you want to work with. For example, vocabulary of system engineering, SysML, whatever. Start somewhere with a methodology. Then you want to federate. Before you federate, you have to define what I call a common library. This common library becomes what these federated parts have to use to be interrelated. If they don't use a common library, they are siloed, you don't know how to integrate them. So common library is a set of definitions with constraints on them that allow you, when you federate your model, you will be able to integrate it back. And we will see how this pattern is very useful in practice. So let's start with the methodology. And here is a very simple methodology, a very simple, the one that we have been talking about all along. Component can contain other components. Component present an interface. This interface can be joined with junction. Junction, think of it as the connector between interfaces, between ports. So an interface is like a port in SysML, and junction is like the connector between ports. And then the junction is traversed by a message. There is some signal going between these interfaces, a message. So every interface can declare which kind of message it transfers in and out. So the transfer relationship has two sub-properties: transfer in, transfer out. They are both subsets of just transfer. And similarly for the join, it's a binary relationship between two interfaces. So you can connect the first one, or the input, the source, with join 1, and the other one with joins 2, but they are both joins relationship. That's the simple methodology vocabulary that you start with here. You say, I want to model these kind of things. So you declare them. Okay. The next thing is we will be creating a lot of ontologies, and we want a way to visualize them. So with the OML Open Caesar technology, you can define a viewpoint for yourself. You can say, I want to see these things as a diagram. And the diagram, if you pick the root component, it looks like this shape. And then within it, there is contained component. Remember, components can contain each other. So you can have, there's a box within a box. And then the interfaces, I will have them as ports. And then the junctions, I will have them as arrows between them. So that when you produce a diagram, you it's like a way to easily see what your model is about. And OpenCaesar has frameworks that allow you to build these things so that you can visualize your model as a diagram. Something like that, for example. Here is a security system architecture with this limited methodology. You have a bunch of, the security system itself has two interfaces. It has a button that you can press to say, oh, panic, there is panic in the room, or there is sensors who can produce events that is received by the alarm system. In both cases, if the alarm system got an event from a sensor, or somebody pressed the panic button, they produce an alarm signal that goes to a monitoring system. This monitoring system will dispatch police or somebody, which will go out of the system to some other external system. Okay? That's a visualization of a potential architecture using this simple vocabulary.
Would this be in a description, or that this is?
Okay, so what you see here is a description. Mm-hmm. And here I want to point out a difference between descriptions and vocabularies. Descriptions are instances. They are like facts about the world. So if you are designing a system and you want to jump into the design, you say, I have a battery one. I have a device one. Device one is powered by battery one. Now you kind of you narrowed down the design. That's it. Or you can do the same thing with vocabulary. You can say, I have this kind of device that can be powered by this kind of battery, and the relationship between them could be multiple devices, could be powered by the same battery. Now, because you can say it can have this, it can have that, you are not narrowing down a particular design. You're leaving, you're kind of describing a class of designs that are acceptable, but you did not narrow down a particular one. When you do description modeling, you are locked in. This is it. This is what you did. Vocabulary allows you a bit of flexibility. It's like modeling a class of things as opposed to a thing. So if you are the builder of the security system, and you want to have an architecture, but you want your vendors, your suppliers, to give you parts that you could then decide how to combine them properly into a real security system. You can model at the vocabulary level to say, I accept any design that conforms to this vocabulary, because vocabulary is a classes with constraints, but I will not jump into the description until later, until when I integrate, then I will make a decision. But at this point, I just want to model vocabulary. And these are the kinds of relationships I have. So to model with vocabularies as opposed to descriptions, it's like saying this. It will say, my security system can have one or more sensor, can have any number of sensor, at least one, but could be more. And these sensors have ports that have junctions that go into the port of the alarm system, which is one. So any system that's valid has one alarm system and has one monitoring system, but can have any number of sensors. And these are the kind of relationships between them. And so what you are doing here is you are creating a set of class definitions with constraints on them that characterize the acceptable solution, the acceptable architecture, without jumping into a particular architecture. If you'd like to open this to the others online, can hear you.
Yeah, sorry. Yeah, just questions about heuristics on ontology design. It sounds, at least from the examples, that the way to go about it is to start from the lowest level abstraction and then extend that out to specific higher level vocabularies. Once you start getting to the point that it's like the description, you need something more general, turn it into vocabulary, keep on going until you hit a point where it's like, okay, now I need just descriptions.
So that's one way of going about it. You can start with a point design and then generalize it, or start with the general design and then go into the specific one. In fact, starting with a vocabulary, there is a technique in system engineering called design space exploration, where you are not sure about the design, but you have some requirements on the design. So you don't jump into a particular design yet. You specify what are the acceptable classes, a class of design, and let some reasoner, some AI, generate candidate designs for you. Okay, design one, design two, all of them conform to your general class of design, but they are different instances, therefore have different characteristics, different performance characteristics. You can take these instances, simulate them, analyze them, trade between them, and pick a nice one. Or maybe you can get insight. Oh yeah, okay. I noticed that the speed that I thought was unlimited cannot exceed this. Let me go back and put a constraint in the classes. Let's generate a new candidate now with this new constraint. So this process of design space exploration starts with a vocabulary modeling, or not a particular solution, because now you've nailed down, you didn't leave any degree of freedom. But with a vocabulary, you can have some degrees of freedom, and then let some system give you candidates that comply. In this case, the design of the security system started with, this is the general architecture of the system. Now, every house is a unique case, right? This house may need 2 sensors, they need 5 sensors. That's why I'm saying in general, it's one too many. I don't want to look myself in.
May I get a quick question on that back one? So on
Yeah.
the relationships that you've got here, these are all in the vocabulary.
In the
right?
vocabulary.
Are these more of the link type relationships, or are these the entity relationships?
No, these particular ones are the simple ones,
Okay,
the simple link. But you could have done it the other way.
you could add
If you have
attributes, make a range.
attributes of them,
Yeah.
you can make them classes.
Okay,
Okay, so you have 3 major categories, right? Sensors, alarm system, and monitoring. So let's pretend we have 3 suppliers, supplier one is giving us two kinds of sensors: smoke sensor and motion sensor. I'm calling this supplier the smart supplier. He provides two sensors, but how do I know that these sensors are correct? They comply to the vocabulary. They are perfect instances of the vocabulary. Otherwise, this supplier is not giving me the correct things to work with as the integrator, right? So he specifically made his smoke sensor extend sensor from the common library, and the interface extend that interface, and the smoke event extend event. This way, I know that these things inherit all the constraints I asserted on the higher level. They inherit them by definition, because extension in class modeling means inherit all the constraints.
So at some point, someone had made, no, that's a new vocabulary that's made by the vendor?
Exactly,
Okay,
by the smart vendor, and they have to relate themselves to the common vocabulary.
Yeah.
Otherwise, they cannot be integrated.
Yeah, so what,
What do you mean?
So this vocabulary is the common vocabulary for home security. The integrator said, okay, suppliers to work to so that I can integrate your work, I'm defining this library for you. This is the architecture at a logical level. Now go and design the sensors, design the monitoring system, security system, but don't just give me anything. You have to relate it to the common library. Otherwise, I will not know whether you did a good job or not, and I cannot integrate supplier one and supplier two.
Right.
So they define a common library and ask every designer, every supplier to come back with a design that relate its design to the common library. So sensors do this, alarm do this too. So in this case, this vendor called the safe supplier, they design an alarm system with the 3 ports expected, interface 4 to the sensors, interface 5 to the panic button, interface 6 to the monitoring. But they added a 4th interface to a speaker. They want their alarm system to have a speaker. That was not in the requirement, right? But that is not a contradiction to the requirement. The requirement did not stop and say these are the only ports. They could have done this if they wanted to, but in this case they left it open. So they came up with a spec that is consistent with the requirement. It goes over the requirement, but it doesn't violate the requirement. So in this case, they said, however, this supplier played it safe and said, and by the way, my speaker is optional. Just to, in case the integrator said, no, I don't want your thing. I don't want some speaker. This will increase the mass. No, this is optional, right? And yeah, and then you can change the library.
Yeah, exactly,
And then you
right?
and the reasoner will tell you whether these suppliers are giving you correct things or not. The monitoring model in this case, so that vendor supreme supplier developed the monitoring system that has the expected 2 ports, but it added a database to log the alarm events. They added another component, and this way they made it not optional. This is required to use our monitoring. You have it comes with a database. That's something we provide, and also the dispatch. They specialize the dispatch to police dispatch. You say at least we have to dispatch the police, and see this symbol means there exists at least. We will dispatch the police. We may dispatch to other things, but at least the police is something we dispatch to.
so that's that little backwards, what is it called? What is a backwards E called? Is there a name for it?
So this one is good for all,
Oh,
and this is there exists.
okay.
So there is at least there's some
Okay.
where that's for every one of them.
Yeah, it's okay. I'll go with just what it actually means. in
Okay,
this sense.
so now the integrator is watching. Yeah, the integrator comes and says, okay, now let's put everything together to create this security system architecture. I will accept the smart sensors. I will accept the safe alarm system. I will accept the supreme thing after verifying that they individually conform to the spec. Let's now integrate them. I will put a junction. So now these junctions are from the integrator, not from the supplier, because the supplier just did the sensor up to here, up to the interface. And this did interface. How the interfaces are connected, the junctions are owned by the security system integrator themselves. They provided these links to connect all the parts together. And now they can run the analysis again to see, does this integration work or not work? So here is their integrated architecture. So remember, sensors are still one-to-many, right? It could be many sensors. But now they go to a particular home, and say this particular home have these 3 particular sensors. I'm calling it a prototype model, or like like in the testing. If they want to test their architecture, they have to create scenarios. So prototype models are like scenarios of descriptions of instances, actual architectures of homes. Let's analyze situations so they can create 1 or more prototypes. And when they actually go to the home and they actually deliver the system, they can instantiate this logic, this architecture into concrete one for the particular thing they want to deploy in. It's a description of the last vocabulary. So this is still a vocabulary. And now, when the testing, it's now a particular concrete thing, they make a description at this point. And then they can use the reasoner. And what could go wrong here in this architecture? Somebody could make a change to the methodology, the very top. They could make a change to the common library. All these parts could be changed, and the integration could be changed. How do you know whether to accept changes or not? The reasoner. If you constrained everything correctly, the reasoner can answer all your questions. We can tell you, yeah, somebody methodology removed the concept interface. Hey, this is like, will break everything, right? Or somebody, no, in the library, somebody decided that the alarm system has a new interface kind that's required. And now the integrator did not account for that. So that will break something. If somebody added a new requirement, alarm system must have a new kind of interface. Okay, now the supplier of alarm system will be broken because their current design doesn't support this new interface. They have to go and they'll be alerted to that and go fix it. Or everything is the same, but the integrator did something also that changed that will broke the reasoning. So the thing is, you need analysis pipeline, a reasoner on your side while you're managing a big project like this, and it can be helpful at all these levels of abstractions.
So on this one, this is sort of like the logical get together, but how do the attributes come into play here? So I'm thinking this is an electrical system, voltages, amperage, right? Frequency that it's running.
So in vocabulary, if you have, for example, the mass, you could assert that the mass needs to be, or the maximum mass needs to be of this value in the vocabulary. But instead of, if you set it at the description, it's like now this particular system has a mass of this. But if you require the maximum mass to this, now this requirement is a constraint. A requirement is like a constraint on something. Any description has to have this maximum mass. Now so you can assert it at the description level as a requirement, or you can assert it this moment the description has this thing. Yeah, right. Okay, so those were the 2 interactive tutorials I planned. There is a set of 6 tutorials that in total that we developed for OML so far that you can learn about them into this site, OML-tutorials. One of them will start with a very simple pizza example, introduces what's OML, what's all the tooling is, and the reasoner. Another tutorial will walk through a methodology development exercise where you actually start developing some vocabularies and then using them incrementally to do description. Another one explores this facet of continuous integration and delivery, and we'll walk you through work. Another one will focus on how you publish reports on GitHub pages. Another one will tell you how to develop a graphical interface over your ontology to hide it from your end user if you like. And then federation is kind of a bit of what I described in the second tutorial, but in a different twist on it. You can I encourage you to have a look at that on your, it says designed to be self-paced. Is there any question for me?
Hi, Maggie, I have
Yeah.
a question. This is going right back to your introduction, actually, before the tutorials. You were talking about the different OML workbenches,
Yeah.
and you said Rosetta is out there in production. It's ready to be used.
Right.
What options do we have if we want to use a web application? I feel like something like a web application version of Rosetta would be easier to fit into a different pipelines that use web applications. So you talk about OML Vision.
So there is
said
OML
that's-
Vision. There is so there's the VS Code option
Yeah.
where you have OML code, for example, that Lorraine talked about.
Yeah. Okay.
OML Vision is the what will let you. It's the equivalent of the serious framework in Eclipse. It lets you define viewpoints.
Okay.
But also the other option is Obsidian, which is also a web platform, Markdown. Everything is web based, and also allows you to define viewpoints with JavaScript. So we are still exploring both options, the VS Code and the Obsidian, to see which one will work better for the end user. Yeah.
Thank you.
All right. If there is no other questions, we can have a break here before our next tutorial.